Hello, dear student. How are you? Is the screen is visible to you? So JNV Bhavnagar is here. Good evening to you. Sorry, good morning to you. Is the screen is visible to you and I'm audible to you? Please make sure that firstly. Okay. So the screen is visible to you or not? Just let me know. The screen is visible to you and I'm audible to you, so that we can start the lecture then. Okay. Just write it in the chat box now. Good morning. Now answer this if you are saying good morning to me. Is the screen is visible to you and I'm audible to you? Okay. So that we can move on in the lecture. So firstly, this is our part 2 of work, energy and power discussion. Okay. So today we are going to see some numericals in based on the work energy and work energy theorem. Right? You are aware about it. So let we just start the lecture. Okay. So basically, what is a work energy and theorem? What does it stand for? So work energy theorem. Work energy theorem tells us about that all the work has to be done, the work done total is equals to the change in the kinetic energy of the system. Okay. You can also write it as work done total is equals to K final minus K initial. This is the formula for work energy theorem. Okay. Now, in this work energy theorem, if you have any idea about the law of conservation of energy, law of conservation of energy, which is nothing but K initial plus U initial is equals to K final plus U final. So when you have applied the conservation of mechanical energy or the law of conservation of energy, it is only restricted to the system only where the conservative forces are acting. ठीक है. But the work energy theorem you can apply anywhere. So it is true. It is true for all kind of forces. Okay, which means if in the system there is some non-conservative forces present, you can also apply the work energy theorem into that. And what type of non-conservative forces you aware about? It is friction. So if in any question the friction is mentioned and there is somehow the possibility to finding the kinetic energy and the work done, so instead of applying the law of conservation of energy that is not applicable for non-conservative forces, you must go through with this work energy theorem. Okay, now let us move on to the first question. A particle of mass m is released in a smooth hemispherical ball from position A. Find the work done by gravity as it reaches the lowest point B. This is the lowest point B. Okay, and this is the highest point from at which this ball is standing, or this particle of mass m is standing. So we have to find out the work done by the gravity as it reaches the lowest point. Since you are aware about that gravity will act downward if the mass of the particle is m, that is given to us, so gravity will acting directly downward to it. Okay, and if the particle come here, then also the gravity will act in this direction. And if the particle is at lowest position, then also the gravity is acting in this direction. So always remember one thing: when you are finding the work of any particular forces, any particular force, you must take the displacement of that force into that direction. Okay, you must take the displacement along that force. Okay, which means you must remember this: always take displacement in the direction of force for which we have to find the work. ठीक है, and in this situation किस force का work हमें निकालना है? We have to find out the work done by gravity, which is mg, the weight of the object. So we have to take the displacement in the direction of this mg. So from here to here it is displaced from this point. This is the highest point and reaches the lowest point. So this distance it has covered. And what is this? This is the radius of this hemispherical ball. Let the radius of this hemispherical ball is r, capital R. So we can say that the work done by mg force is nothing but force dot product with displacement. Here the force is mg dot product with displacement here is r, because this is the topmost position, and from this to the lowest point it has covered a distance r in the direction of mg. Okay, so it is mg dot r. Now if you open this dot product, what you will have, it is mgr cos theta is the angle between this force and the displacement. Then what is the angle? Displacement is also in the downward direction because ball is moving downward, and this gravity is also acting in downward direction. So the angle between the force and the displacement is 0 here. So cos 0. Now cos 0 is nothing but 1. So mgr cos 0 into 1. So we have work done by mg force is equals to mgr. So from this question, we have understood that we have to take the displacement in the direction of force, applied force, for which we have to find out the work. Got it? Okay. Now, I hope this question is clear to you. Now, I will move on to the next question. If you have any kind of doubt, you can ask in the chat box. Okay. Now, if the force, the next question is if the force, just the advancement of that question. If the force F vector is equals to 3x I cap plus y square j cap is acting on a body moves from 1 to 1, which is 1 meter, 2 meter, 1 meter. These are the coordinates. Okay, x, y, z coordinate. 2, 3, 3, 8. These are also the final coordinate of position. Then find the work done due to the force. Now I am giving you 1 minute to solve this question. And it is a very simple question. Do not afraid of this expression, this 3x I cap y square j cap. Just find out the displacement vector. Okay? And then take a dot product of it with f. Then you will find the work done. Okay? So try to solve this question. Okay? So are you trying to solve this question? JNV Bhavnagar. Okay. So the expression given to you, force is equals to 3xi cap plus y square j cap. This the initial position coordinate given to you, let's say the r1 r1 vector you can form from it, because if x y z are the coordinates, then the position vector will be x I cap. Just put the I cap, j cap, and z cap, y j cap, z k cap. Okay, so for that, if the coordinate is given to you 1 to 1, so you can write it as I cap, because 1 into I is I, plus 2 j cap plus k cap. Similarly, the final vector R2 vector is 3i cap plus 3j cap plus 8k cap. Now, if in the coordinate system, this is R1, the initial coordinate, and this is R2, the final coordinate. So what is the displacement? The particle has displaced from R1 to R2. So you need to find out final displacement vector, which is r vector, and it is given by r2 vector minus r1 vector. Okay, got it? This is the r vector. You can apply the triangle law over here, triangle law of vector addition. So r1 vector plus this r equals to r2 vector, r1 vector plus r vector equals to r2 vector. So from that you can say this r vector is nothing but r2 vector minus r1 vector. Okay, now we have to find out the final displacement. Displacement. So displacement here is r vector, which is r2 vector minus r1 vector. Now r2 is 3i cap plus 3j cap plus 8k cap minus r1 is I cap, 2j cap or k cap. Now take the difference of it. It will become 2i cap plus j cap, because 3j minus 2j will be plus j, plus 8k minus k. This is plus 7k cap. Okay. So this is the r vector you are having. This is the displacement vector. Now work done is given by force dot product with displacement vector. Now what is force vector? Force vector is 3x I cap plus y square j cap dot product with displacement vector, which is 2y cap plus j cap plus 7k cap. Okay. Now I have told you in the previous class how to solve a dot product like this. I dot I you have to only consider the same vector, you have to consider only. All the other vectors present in the combination will become zero. Like I cap dot j cap will become zero, I cap dot k cap will become zero, j cap dot I cap becomes zero, and j cap dot k cap becomes zero. So only 3x I cap with 2 I cap and for y square j cap with j cap you have to consider. Okay. There is no coordinate, there is no component of k vector in force, so we will not take that. So it is 3x I cap dot I cap will become 1 plus y squared j cap dot j cap will become 1. So it is y square. So this is the work done. Okay. In this question, there are lots of variation that could be possible. He can ask you, the one can ask you about that, find the work done for the position 0 to 2 or 0 to 3 or like this. Okay. This is all the possibilities that can be asked, because here the work done is a variable one. Okay, got it. Oh, if you have any kind of doubt, you can ask. Now this is the latest question of gmean coming in 2020. So try to solve it. It is the same as given in the previous, because it is but I must say that it is the easier one from the previous question that I have taken. Okay. So try to solve this question. I'm giving you 30 seconds for it. Okay. Why the attendance is too low? Are you guys on some kind of vacations? That is why you are not attending the lectures. And please be responsive. Huh? Please do response. So now in this question, consider a force F vector is equals to minus xi cap plus yj cap. So a force vector is given to you. The work done by this force in moving a particle from point A102 to B01 along the line segment. All the quantities are in SI unit. So we have to find out the work done by this force moving a particle along this line. Okay. So if we are able to find out the coordinate, if we are able to find out the coordinate of this line vector, which is similar to the displacement vector, because particle has started from here, point A, and reached to the final point B. So we have the coordinate, both of them. So what we can do, we can find the displacement vector, and then we take the dot product with the force vector. Okay. Now, in this question, formula that we are using is work done is equals to force dot product with displacement. Now we have to find out the displacement vector. Displacement vector is the, I'm just writing the simple one. Take the difference of x coordinate, multiply with I cap. Okay. So here The particle initial x coordinate is this. So xi, yi is given you as 1, 0, and x final, y final is given you as 0, 1. Okay. So displacement vector is delta xi cap plus delta y j cap. ठीक है. What is delta x? It is x final minus x initial I cap plus y final minus y initial j cap. Okay. Now, what is the final coordinate of x? It is 0. So 0 minus, what is the initial coordinate? It is 1. So 1. 0 minus 1 I cap plus similar to y final is 1 minus 0, the value of y initial. Okay. So you have under root 2. The answer of this question, let me find out and then we will check. Okay. Very good, you are solving this question. Okay. It's good for you. So it is minus I cap minus, sorry, plus j cap. This is the final displacement vector we have. So work done here is f dot d. F vector here is minus xi cap plus yj cap, and it is minus I cap plus j cap. So we can dot product it as minus x minus minus plus x plus y. Okay. Y dot j is x plus y. So work done we have as x plus y. Now, one thing that we are provided here with is that the limit, the x coordinate varies from 0 to 1 and the y coordinate is also varying from 0 to 1. Okay. So to finding the final work done by this force, what we can do, we can just take the differential work dw, which is the final work we have is at is it. So we can take it as x dx plus y dy, and we can differentiate it from 0 to 1, and it is also 0 to 1. Okay. Because if I take it here, if I take this here, so there is no meaning of this limits. Okay. Got it. So we have to find the work done along this line segment. Now if you can integrate it, it will become, it is also integrate, so it will give you the total work done. So work done here is 0 to 1 x square by 2. It is also x square by 2. 0 to 1, 0 to 1. So we have 1 by 2 plus 1 by 2, which is equals to 1 unit. So work done here is 1 unit. Okay. So how you are getting this under root 2? How is this you are doing this? You have taken this d as it is now, minus I cap plus j cap. Huh? Or is there any mistake that I am doing? This is the work. Okay. If you take the displacement vector as dr, so it here is dx I cap plus dy j cap. Okay. And if you multiply it with force vector, take the dot product of it, fdr, so it will become uh, minus x I cap minus x dx plus y dy. Okay. And if you differentiate it If you integrate it from 0 to 1, 0 to 1, then also the same result you are getting. Okay. Okay. So I hope you are clear with this concept. Any kind of doubt you can ask immediately. Now, okay, let me just again solve this for you, the better understanding of your. Here it is 1 0 and it has moved to 0 1. Okay, because this force is variable, F is minus xi cap plus yj cap. So this force is variable, so that we have to take a very small displacement. For that, the force will behave as a constant one. Okay. So the displacement vector, differential displacement vector, dr vector, we can consider as dx I cap plus dy j cap. Okay. Now, now the dw, the small work for this dr displacement is f dot dr. F vector is minus xi cap plus y cap yj cap dot product with dx I cap plus dy j cap. Okay. Now, if you take the dot product of it, it will become minus x dx plus y dy. And if you integrate it, you will get the total work done. This is the total work done. So if you put the limit, x is varying from 0 to 1. This is the limit of x, 0 to 1. And y is also varying from 0 to 1. So it is minus x square by 2, 0 to 1, plus y square by 2, 0 to 1. So it is minus 1 by 2 plus 1 by 2 will become 0. So the answer to this question is 0. Here the work done by this force will become 0. So it is not under root 2, not 1. It is 0. Okay. We have take a small mistake over here. Instead of putting this minus x, we have just put it as x. Okay. So I have corrected it here. So you can take the note of it. Okay. So work done in this case is 0. I hope you are clear with this now. Have you got this? JNV Bhavnagar. Now you got this? Please reply in the chat box if you have any kind of doubt in this. Okay. Now, this is a question. Okay. This is the question. I have so two blocks having mass small m and capital M are placed on a smooth surface and a force F is applied on the system. Now find the work done by the normal reaction. I have taken this question to make you understand how the different forces, what will be the work done by the different forces, like the normal force. Firstly, we are going to see. Before starting that, I will also share some tips about the work done. Okay. So when will be the when work done is 0. तो work done 0 कब हो सकता है? Work done is equals to f d cos of theta. So work done is possibly 0 when there is no force acting on the system. If f is equals to 0, work done is 0. Like you are sitting on your desk or on your sofa from where you are taking the lecture. You are just sitting, there is no force acting on you instead of gravitational force. So the work done by any forces which is not even present there is 0. So when you apply no force, the work done will be zero. Now the second scenario will be when displacement is equals to zero. Then also the work done is zero because it is the product. Now in this case, like you are sitting, sorry, you have seen some labor worker, they put some load on like this and take it to the another place. Now if they are moving in a horizontal direction, if they are moving on a horizontal plane, like this is the worker and he's holding some weight on his head. Okay, so in this scenario, if this worker move from here to here, if this worker move from here to here with some displacement, it has covered D. Okay, now in this scenario also there is a weight and there is a displacement. So what will be the value of work done? In this case, work done is zero. You will say how the work done is zero? The work done by the weight that is acting down to the head is zero. Why? Because the weight of the this person is also acting downward, and weight of this, whatever the weight he has put, is also acting downward. So the total weight is acting downward, like say it is capital Mg, and displacement it is in horizontal direction. So what is the angle between them? Angle between them is 90 degree. Okay, so in this scenario work done will be zero because cos 90 is zero. This displacement is zero when work done is zero. How? When? So let's take an example of stairs. So these are some stairs. When you put your feet on the stairs, okay, so there is a normal reaction coming. Although there is a normal reaction, force is there, but is your feet is moving when you climb on the string on the steps. जब आप सीढ़ियों पे चढ़ते हो तो क्या आपका पैर मूव करता है एट दैट इंस्टेंट? ठीक है, try this today and look what happens. When you try to climb up on the another step, the back foot of yours will remain stationary. Although there is a normal reaction is acting there, but there is no displacement. So in this case, the displacement is zero. So you can say there is no work. Okay? So this is the example of this situation. Okay. Now the third scenario that could be possible is theta is equals to 90 degree. The work done will be zero. As I've already discussed you this situation. Okay. Now move on to this question. We will move to this question and let's see will what will be the solution, possible solution of this question. Okay. Now there is a constant force F. The two block having mass M and capital M. This is capital M and this is small m are placed on a smooth surface and a force F is applied on the system. Find the work done by the normal reaction. This is the force and this is the surface on which they are moving. Okay. Now the normal reaction will acting in the upward direction. This is the normal reaction for this block provided by this surface. On this block also, let's say this is N1 and this is N2. Now there is one more reaction. There is one more normal reaction which is acting on it. And what is that? What is that? If I just reverse the direction of this force, this block pushes this block, this small m mass pushes this capital M mass. So there is a normal reaction in this direction also. It is let's say n. Now, if you see the work done by, if you see the work done by the normal force we have to. So for N1, we are going to calculate firstly. For N1, the block will be displaced at a distance d over here. This is the displacement d. Now, for N1, the work done by N1 is equals to N1 dot d. N1 is nothing but the mg. Okay. So you can say that mg d cos, what is the angle between mg and d, or normal reaction or d displacement? It is 90 degree. As I've already told you, normal reaction is at a 90 degree from the horizontal direction. Okay. So the force will become zero. The work done will become 0 for N1, and same goes for N2. So the work done for N2 will also become 0. Okay, got it? Now, if you talk about this force, let's say the FBD of small m, if I draw, this is small m block, this is the force acting capital F. Instead of drawing in this direction, I have drawn it in this direction at that point. Okay. So because of that force, this small m mass block will try to push this capital M mass block in this direction. So in reaction to that, it applies a force in this direction. Okay. So there is a normal reaction would come. This is normal reaction. And let's say the displacement is d in this direction. The displacement is d. Now what is the work done by this n force? Okay. Now you can see that for capital N, ठीक है, force, the work done will be n dot, sorry, n dot d. Okay, got it? Now n in is in this direction and displacement is having in this direction. Okay, so they are equal and opposite. This is n, this is d. They are equal and opposite, having an angle 180 degree between them. So you can say that nd cos 180. Okay. So from here you can say that it is nd minus nd, because cos 180 is minus 1. Okay. And if the block is not accelerating and moving together, so we can say that if blocks are moving together with no acceleration, so you can say that this normal reaction is always equals to the force applied, this in the horizontal direction. Okay. So for that you can say that work done is nothing but equals to minus F dot FD, not dot, FD only. So I hope you are clear with this question. Okay. If you have any kind of doubt, you can ask. I don't think so you are having any kind of doubt in this. Now, move on to this question. So in this lecture now, we are trying to find out the work done by different forces. Okay. Work done by different forces. How the different forces will act. Okay. Now, A block of mass m is suspended from the ceiling of a lift by a massless rope. The lift is going down with an acceleration of g by 2. Find the work done by various forces on the block as it got down at a height h. So let's say initially the block is at here. This is small m mass block. The tension T will applied on the upper direction, and the weight of the block is acting in the downward direction. And this block is accelerating at g by 2 because the lift is moving downward. From this point, it has moved to a distance h, yeah, to a height h. So this height is h. This is mg, and this is again tension. Okay. So here there is only two forces acting, which is firstly it is tension and another is mg. Now, if I talk about what is the magnitude of this tension and all, okay, so we can say that according to firstly we have to find out this tension. What is this tension is? And we are very clear from our question discussion on Newton laws of motion that how to find this tension. The acceleration is given to you, the forces are given to you. Just draw the FBD that I already drawn and apply the Newton second law. Okay. So apply Newton second law. And what is that? It is F is equals to M. Now, what is the net force? You have to take mg positive because it is in the direction of acceleration. So it is mg minus t is equals to m into what is the acceleration? Is g by 2. So tension here is nothing but take t here and mg g by 2 here. So tension you will have as mg by 2. So the tension will become mg by 2. Got it? Now, firstly, we will see let we will discuss the work done by tension force firstly. Okay. So work done by tension. So work done is equals to tension dot product with displacement. So tension here is mg by 2. Displacement is h, but be careful with the directions. Be careful with the angles. H we have taken in the downward direction because lift is going downward, the block is moving downward, and the tension is acting in the upward direction. So they have an angle of 180 degree between them. They are equal and opposite. So 180 degree angle means cos 180 you have to take. Cos 180. Cos 180 will become minus 1. So the work done by tension force here is minus mg h by 2. Okay. Now, work done by the second force that is left, work done by mg. So work done we can take mg. This is the net force acting. Dot product with h, and the angle between them is because mg is also in downward direction. Displacement is also in downward direction. So mg and h has an angle 0 in between them. So cos 0 will become, it is mgh cos 0. Work done here is mgh only by the mg force, and this work done is by tension force. Okay, got it? Or if you want to find out the total work done, these are the various force. It can also ask that find the total work done. So total work done will be work done total will be W1 plus W2. There are only two work here. W1 is minus mgh by 2 and W2 is mgh. So it is mgh by 2. This is the net work done. Got it? I hope you are clear with this. Huh? Is any kind of doubt in this question? If not, then we will move forward to the next question. Okay. This. So if the question is not clear to you, that is why you are saying no, sir, or the question you have no doubt, that is why you are saying no, sir. So please make it clear. If you are having no doubt, na, so write it no doubt, or simply you can write ND. Okay. Now this is a road. This is a small object. Okay, okay, got it. And there is a force F acting on it. Now a small object of mass m is moved over a rough surface. The force which moves it along the dotted path is always tangential to the curved path. You will see this is the curved path. And if the object moves with negligible speed, then find the work done by the force F moving the block from A to B. This is point A and this is point B. The coefficient of friction of the object and the curved surface is mu. So here the friction is present. Okay. So what we will do, we will take the small cross section. This force that is acting is always tangential. Okay. Now the displacement, the path that we have taken is not constant. Okay, is not constant. It is curved. Like the each and every time the force is changing the direction, but in each and every situation it is always along the displacement vector, because it is a tangential force which is always tangential to the curved surface. Okay. Now if we take the very small cross section of this, so this is seems to be a, let we take this cross section, this. Okay. So if I take a very small cross section, it will definitely feel us to be a, it will definitely feels a triangle. This curved path will appear to be a straight line. Let's say this is the ds. In x direction, this is dx, and in y direction, this is dy. And this angle is theta. Okay. Since this force is always acting, this force is always acting tangentially, so this force vector is in the direction of this ds vector for this small displacement. Okay. Now this object moves with negligible speed, means there is no speed. Okay. So v is equals to 0. If v is equals to 0, then the kinetic energy of this block will be 0. Got it? So we can say that work done in the work energy theorem, work done is equals to change in kinetic energy. And if the kinetic energy is 0, so the work done by all the forces will be 0. Here, the work done by only we have, if I draw the FBD of this system, the mg force is acting downward. This F is acting tangential, the F that we have applied, and there is a opposite to that, there is a frictional force, because this curved surface, the coefficient of friction is always provided to us. Okay. So here you can say that work done by, just a second, work done by friction plus work done by capital F, let's say this is friction, plus work done by mg force is equals to 0. Okay. So we will take that because the path is not a straight line. Path is not a straight line. So we would have to deal it with a straight one. So we have considered it a very small displacement, and then we will integrate. Okay. Now let this height be h and this length be L. Okay. Now the frictional force, frictional force is nothing but this frictional force is nothing but mu times n, which is mu mg. Okay. And if the block is moving upward, the friction will acting downward, which means for each and every displacement, the friction will act opposite to the displacement. The angle between them is the angle between them is not uh, not a 0 degree angle. It is 180-degree because they are equal and opposite to each other. So you can say that the small work for this ds displacement we are finding out, and this frictional force is always acting in the direction opposite to this ds, because friction always act to the contact. Okay, and since this force is a tangential force that we are applying, so the friction force that is opposite the motion is also a tangential force. So this is the direction of friction force. Okay. So mu n, you can say mu n dot ds, एंड डॉट ds को रिमूव करने के लिए cos एंगल लेना पड़ेगा, which is nothing but माइनस, ठीक है, माइनस mu n ds. Okay. So after that, till now you have clear with this. We will discuss this question in our next session. Okay, because the class is over then. So thank you so much for being attentive. Okay. I will discuss this question in the next session. Okay. Thank you so much.